Okay, should I start? Okay, so in today's talk, I will introduce you to my PhD research, and specifically, I will be talking about system identification and damage detection at first, and then I will continue with sensor fault diagnosis in civil infrastructures. So let's get started. So at first, a few words about myself. I started my academic journey in Greece, my home country, where I got my diploma in civil engineering at Democritus University. And then I moved to Denmark, where I obtained my master's in structural engineering in 2021. And from then on, I started a PhD at DTU in structural dynamics and structural health monitoring. And of course, this September, I'm very glad to be part of the group until the end of November as a visiting PhD student. A few words about my team as well. First of all, my supervisor, Rune Brinker, who is mostly famous about the FDD technique, the frequency domain decomposition for model identification. He's also a co-author of Introduction to Operational Model Analysis, the most cited book in the field of OMA, and he's also a co-founder of the Geomatic conference. Unfortunately, last year, Rune decided to retire from the university, so he's no longer my supervisor. We still have some contact, but we don't work together. I mainly work with Sandro Amador on the left, who is an assistant professor at DTU, and his research field lies in structural health monitoring, operational model analysis, and damage detection in civil structures. And then Holger Kos is an associate professor. He is the person that replaced Rune in the supervision team. So he's an associate professor at DTU. He's also working with structural dynamics, but he has a wind engineering background. So now, after this introduction, let me start with today's agenda. My PhD is mainly based on experimental work. So in this first part, we'll be talking about a long-term monitoring, an automated SHM scheme that we have developed for system identification and damage detection. We use data we collect from an experimental model under ambient vibrations and different environmental conditions. Then in the second part, I will be talking about another interesting topic of sensor fault detection. So it's quite important to know the reliability of data we obtain from our sensors. Because all the methodology that we are using in the different schemes are based on the quality of those data. And in order to do that, we propose a method to identify errors within sensor networks. And finally, in the last part of this talk, I will be talking about some future research activities and some main goals and the main goals of my PhD research. So let's start with the monitoring. The SHM scheme that we follow is based on four different steps. First of all, of course, we have the raw vibration measurements from the different structures. And then we apply operational model analysis to identify the model properties, meaning the natural frequencies, damping ratios, and mode shapes. So we would like to obtain those parameters in order to make conclusions about the structural condition of the monitored system. But we are very well aware that there are different parameters that might affect the model properties, such as the environmental and operational variability. So in order to make those safe conclusions, we need to eliminate those parameters first. And after we do that, we can proceed to damage detection or other techniques. So as I said before, we apply this concept in an experimental study. We have this monopile specimen at the DTU campus, which consists of a wooden mast and a steel topside. the idea of my PhD is that I would start with this experimental model, and then at some point during the PhD, I would get some real data from offshore platforms, from companies that collaborate with PPU, but that never happened. So we're kind of forced to continue with this experimental model. Anyway, the measurement system consists of 4 3D sensors called geophones that we mount on the steel topside that you can see on the left. And then we split the monitoring campaign into 20-minute measurements. So we get approximately 72 different data sets per day. And then the wooden mast, we use wood so we can go out there and damage the structure and then be able to apply different damage detection techniques to apply those damages. Specifically, what we do is we induce some cuts, as you can see there. We start from 2 millimeters, and then we increase the cut depth every 2 days by another 2 millimeters. So we go from 2 to 4, 6, up to 10. And then in the last day of this damage period, we go and we damage the structure in the other side, but this time directly to 10 millimeters. So this is the concept. And then the model identification, we see that the natural frequencies of the first 2 modes vary around 1.2 hertz in the undamaged state of the structure. And then when we introduce these cuts, the gradual cuts in this direction of the mast brought a gradual decrease in the natural frequencies of the first mode, whereas the other cuts, the sharp cuts in the other direction are mainly correlated to a sharp decrease in the natural frequencies of the second mode. And then, as I said before, so this is the first indication that there might be a damage presence because we know that the stiffness is associated with the natural frequencies. So this drop in the natural frequencies alert us that there might be a structural degradation, but as I described before, we would like to eliminate the environmental parameters first in order to make safer conclusions, and we do that by applying by using principal component analysis. So what we actually do here is we take the identified natural frequencies in Y, and then we calculate the covariance matrix and use singular value decomposition of this covariance matrix. So we obtain the singular values and the singular vectors in U. So PCA states that most of data's variance is explained in the first singular values. So if we take the first, say, M singular values and the corresponding M columns from U, then we can define the PCA estimate Y hat, where most of the variability that we see in this plot should be included over there. So we would like to isolate the variability from the environmental parameters in Y hat. So in the next step, we just exclude it from the identified natural frequencies by taking the residual error. So if we do that, here we see the example. So we split the monitoring campaign into 3 parts: the training part, the validation, and the prediction period, where we apply this methodology I described before in the training part. So we calculate the covariance matrix. We take the first M principal components as they explain 99% of the variance, most of the variance of the data we have, and then we calculate the PCA estimate. And what we see here is that our model is correctly validated over the yellow part, but of course in the black one we see that it can no longer describe the actual evolution of the natural frequencies. So this is something that we expect to see, of course, because we trained our model in the training part where no damage where we have no damage presence, and of course the model cannot predict, doesn't have the ability to predict the damage cases that followed. So this is indication of the damage presence in our experimental model. And then if we go one step further in the methodology and calculate the residual error and finally the corrected values, if we plot these corrected values, which represent the natural frequencies, but now where we have eliminated the environmental effects, we see that they have a way more stable evolution. The black curve has a way more stable evolution, and we can see it more clearly if we zoom in the last part, where after the application of PCA, most of this fluctuation due to the environmental effects is now gone. And this is also confirmed by the standard deviation, which is of these values, which is reduced by 50%. So now we have corrected the identified natural frequencies, and we would like to apply a damage detection scheme to identify the damage cases we induced in the wooden mast. For that reason, we use control charts, which are a statistical tool for quality control. And what we actually do here is we calculate a t-squared index for all the observations that we have, and we compare it with a control limit UCL. And what we see here is that for the undamaged state of the structure, only 0.1% of the observations exceed UCL, but when we started damaging the structure and keep increasing the cut depth, we see that more and more values of this t-squared index exceed the limit, and actually after the 6 millimeters of those cuts, all of these values exceed UCL, leading to a successful damage identification. So that was the first part. Let me now move to the second one, which is the sensor fault detection. As I said before, we would like to make sure that the data we obtain are reliable, and we propose a method here in order to identify errors within sensor data. This method is proposed is based on the rigid body assumption, which states that any limited part of any structure, like the top side of an offshore platform, for example, or simply the top side of our little specimen, can deform as a rigid body. And that means that if this body can move freely in the 3D space, it has 60 degrees of freedom that can describe its motions, each motion, 3 translations and 3 rotations. And if we take this top side, we also, of course, know where we have placed our sensors. So we have 4 3D sensors, meaning 12 channels, 12 signals. So now we can establish a relationship between the measured response in Y and the actual DOS movement in D. We can solve this equation in a least square sense. So we obtain D hat. And then the concept of this method is that since we consider this top side as a rigid body, we have more signals than the measured quantities. In simple words, we have 12 sensors, 12 signals to measure 6 degrees of freedom. So this system of equations is overdetermined, and that means that if we have an error in some signals, or we have a faulty sensor, we can simply eliminate it and continue the analysis without problems. So now, if we take this estimate for D and put it in the first equation, we obtain the so-called synthesized signals, which are the signals we approximate, where we assume that most of the error, most of the sensor noise is now is eliminated. So what we have is 2 sets of signals: the measured responses and the synthesized signals. Where if we take those and gather them, then if we take the residual between those, we define the error estimate, which is the primary tool to identify errors in signals. So let us see some applications. Here we have the most common errors in vibration testing. We can have bias, for example, where we have an offset in our signal, or we can have bias where the signal is amplified by a factor B, or we can have a complete failure, for example, in this case, where the sensor stops working. So what we do here is that we take those errors and we try to simulate them in the gathered responses that we have from our experimental model. So for example, here you see that we have a bias in channel 12, a complete failure in channel 6, and so on, so forth. And here we have some results. On the upper left, we see the case where we have no errors in signals. And so we see that the time evolution of the error estimate remains relatively low. But when we introduce some faults, like bias in signal 3 or gain in signal 2, we get those peaks in the error estimate in the corresponding time window where the fault is present. And the same thing applies in the next row, where we have the drift, the constant failure, or the noise residual. So we conclude that this error estimate over time is an effective tool to identify those errors in the signals. But we are not really satisfied with this solution because, as I said before, we get 12 signals every 20 minutes. So it's not optimal to go through every signal that we get to estimate, to see if we get some peaks in the error estimate. We would like to automate this procedure, and we do that by an outlier detection, where we calculate the standard deviation of the error estimate for all the signals. So we have one plot instead, and what we see here is that in the upper figures, the standard deviation is around 0.2 in the power of 10 minus 3, where we have no faulty signals. But when we introduce errors, like for example, the gain in signal 2 or the complete failure in signal 10, we see that the standard deviation peaks. So we identify those signals as the faulty ones. And we also notice here that the rest of the channels are affected from these errors, and especially the neighboring ones. But if we go ahead and eliminate those from the analysis, then we see that the rest of the channel, we can continue the analysis without problems, and we see that the standard deviations of the other signals return to an accepted range. Okay, and now the last part about the future research activities and the next steps of my PhD research. Let me start with the first part of monitoring. We saw before that we have this monitoring campaign, and here we notice that this campaign only lasts for 1 month. So what we want to do here is to extend this monitoring campaign to at least 1 year of monitoring. And we have already started doing that. So we started this January to monitor this specimen again. And here I have some data until May. So we have 5 months of data of natural frequencies here. And what we see, if we repeat the procedure of the environmental model, we want to we once again train our model. In this case, I used data from less than a month, and we get this result over here, where we see that again most of the variability due to environmental conditions is gone. So our plan here is to have a longer monitoring and also to train our model in a longer period. So we include the seasonal variability, the cold temperatures during the winter and the hot ones during summer, and we build an effective environmental model. So then we can base our damage detection or other ideas that we might have from then on a very robust foundation, let's say, of this solid environmental model. And then in the second part about the fault detection, we obviously want to assess the effectiveness of the method. So in other words, we would like to assess how big, let's say, how extended the faults would be. meaning this P parameter. So here I have an example of the gain detection where we test different values of the gain coefficient B to see the effectiveness of the algorithm. And what we see here is that when we have a gain with a coefficient bigger than, let's say, 2 or maybe 1.7, we get a high success rate, whereas when the coefficient is around 1, it's not that effective. And we would like to do the same and assess how long, for example, this bias or this gain should be, or how many outliers should we have in order to have an effective fault detection. And finally, we would like to expand this method. So we don't want to rely on the rigid body assumption anymore. We would like to extend this method to a more general case where instead of using this transformation matrix, this expression t times d, we will expand this methodology and use the mode shapes and the model coordinates instead. And that means if we get rid of this assumption of rigid body deformations, we can go to a more general case and include more complex geometries. And I think that wraps it up for today. I would like to thank you very much for listening.